When you think about a physical border
Yeah.
here on Earth, there is a certain comfort in the absolute geometry of it.
Right, it's very defined.
Exactly.
Mm-hmm.
You build a wall or, you draw a line on a map, you set up a checkpoint, and you can say with absolute certainty, this side is ours and that side is theirs.
Yeah, it's a binary reality.
Right. You are either in our sovereign airspace or you are not. You are either trespassing or you're safe.
It is a very terrestrial, two-dimensional way of looking at security, really. I mean, we humans like the idea of a locked door.
Oh, definitely.
It makes us feel secure because historically a locked door meant you had control over who could see you and who could reach you.
But then you look up. You look up at the night sky and you realize that the ultimate high ground, the space domain, it doesn't have walls.
No, not at all.
Doesn't have checkpoints. We're talking about a diagnostic and operational landscape that completely shatters that whole terrestrial illusion of a locked door.
It really forces us to realize that the locked door is essentially made of glass, and anyone with the right vantage point is just peering right through the skylight.
That is such a creepy visual, but so true.
The concept of privacy, or operational security on a national scale, it fundamentally changes when the threat isn't coming across a border, but is orbiting directly overhead at 5 miles a second.
Well, welcome to the Doctrine Deep Dive. We are so glad you're joining us today.
Yes, absolutely.
Our mission in this deep dive is to explore how space-based systems serve as that ultimate high ground for intelligence, surveillance, and reconnaissance.
It's a massive topic.
It really is. We're going to detail the physics and the mind-bending capabilities of these systems, their very real limitations, and the major agencies that actually control the cameras and microphones pointed at the Earth.
Right.
And to ground this whole conversation, we are pulling our insights directly from two foundational texts. So we are looking at the United States Army Space Reference Text, March 2026, and Joint Publication 314, Joint Space Operations.
And those texts are critical. I mean, they lay out the actual reality of modern military and intelligence operations.
Right, they aren't just theoretical.
Exactly. They detail exactly how the military, the intelligence community, and increasingly the commercial sector operate in this domain.
And that commercial aspect is so crucial.
It is. The days when only one or two superpowers could afford that godlike view of the Earth are just gone.
That is the reality you have to keep in mind as we go through this deep dive. Space gives us this incredible vantage point, but the monopoly on that high ground is rapidly disappearing.
Rapidly.
So whether you are a military planner trying to move troops without being seen, or you are just insanely curious about modern surveillance and how the world is watched, this information is absolutely critical.
It applies to everyone now, really.
Let's start with the concept of that glass skylight you mentioned earlier. Because according to the reference text, the primary strategic advantage of the space domain is overhead access to denied regions without violating another nation's sovereign airspace. Let's kind of dig into the legal and physical reality of that.
The legal framework is fascinating, mainly because it is based on physical limitations. I mean, on Earth, if you fly an aircraft equipped with a camera over another country without their explicit permission...
You've committed an act of aggression.
Exactly. You have violated their sovereign airspace. And under international law, they have every right to shoot that aircraft down.
Which we have seen happen historically with reconnaissance planes.
Oh, plenty of times.
Because airspace is just an extension of national borders. It goes straight up.
But it doesn't go straight up indefinitely into the cosmos.
Right.
There is an internationally recognized, albeit sometimes fuzzy, boundary where the Earth's atmosphere ends and space begins.
The Kármán line, basically.
Yeah, basically, yes. Once an object is in orbit, meaning it is traveling fast enough horizontally that as it falls toward the Earth curves away beneath it, it is in an internationally recognized global commons.
Kind of like international waters.
Just like the high seas, no one owns space.
Meaning a satellite can pass directly over the most heavily guarded, top secret, heavily defended military facility on the planet, and technically no laws are being broken.
Not a single one.
The nation below cannot claim their airspace was violated because the satellite isn't in their airspace. It is in orbit.
And that provides unprecedented, unhindered access. You don't need a diplomatic passport or flight clearance to look down.
Which is a huge advantage.
It is. But building, launching, and operating those satellites, and then actually doing something useful with the mountains of data they collect, is an extraordinarily complex endeavor.
I can only imagine.
It is arguably the most complex logistical and engineering challenge humans undertake. It is certainly not managed by just one group or one office. The Department of War relies on a triad of major agencies to handle space intelligence, each with a very specific complementary role.
So let's explore that triad, because like you said, you can't just slap a digital camera on a rocket and call it a day.
No, definitely not.
The first organization the text outlines is the National Reconnaissance Office. Their mandate is to design, build, and operate the nation's reconnaissance satellites.
They are the architects, the engineers, and the orbital drivers. And we really have to appreciate the sheer hostility of the environment they're designing for.
Yeah, space is not friendly.
No, it's incredibly violent. When the National Reconnaissance Office build a satellite, they're building a machine that has to survive the massive, violent acoustic vibrations of a rocket launch.
Oh, just the shaking alone would destroy most electronics.
Exactly. Then it has to unfold itself in a complete vacuum.
And the temperature swings up there are wild, right?
Extreme. The side of the satellite facing the sun might be hundreds of degrees above zero, while the side in the shade is hundreds of degrees below zero.
Wow, at the exact same time.
At the exact same time. The materials expand and contract constantly. Yet, despite this, the National Reconnaissance Office has to ensure that a mirror the size of a school bus remains perfectly aligned down to the nanometer.
While traveling thousands of miles per hour.
Right. They are responsible for the health, the positioning, and the functioning of the hardware. They make sure the eye is open and looking in the right direction.
But having an open eye is only step one, right? Because a satellite beaming down ones and zeros isn't actually intelligence. It is just raw data.
It's just a really expensive photo album until someone looks at it.
Exactly. And that brings us to the second agency in the triad, the National Geospatial-Intelligence Agency. Their job is to exploit and analyze the imagery and the geospatial data. They are the ones who visually depict the physical features and the activities happening on Earth.
To put it in perspective, the Reconnaissance Office might downlink a massive raw data file, like a digital image covering hundreds of square miles of a coastline. But an image is just an image. It requires a human or an advanced algorithm from the National Geospatial-Intelligence Agency to look at it, interpret the shadows, measure the structures, and determine the context.
What kind of context are they pulling from a flat picture, though?
Well, they might look at a cluster of buildings and notice that the shadows indicate a specific height, or they might measure the width of a newly poured concrete pad and cross-reference it with known dimensions of enemy ballistic missiles.
Oh, wow. So they are looking at the tiniest details.
Absolutely. They are the ones who determine that what looks like a harmless civilian warehouse is actually a newly constructed submarine pen. They turn raw pixels into actionable geospatial intelligence. They map the physical reality of the battlefield.
Okay, so the first agency builds the camera, and the second agency interprets the photograph. That covers the visual side of things. But we aren't just looking at the Earth, we are also listening to it.
We are listening very closely.
And that is where the third agency comes in, the National Security Agency. According to the texts, they collect signals from space, processing and analyzing them to exploit foreign communications and electronic emissions.
The Earth is incredibly noisy in the electromagnetic spectrum. It is glowing with radio waves, microwave transmissions, and radar pulses.
Just buzzing with energy.
Exactly. And the National Security Agency operates in that unseen spectrum. While the geospatial analysts are looking for physical structures like tanks or buildings, the signals analysts are hunting for invisible energy.
Like intercepting phone calls.
Intercepting the communications bouncing around a battlefield, or identifying the specific frequency of an adversarial radar system scanning the sky.
Okay, let me make sure I have this workflow straight, because it is a massive division of labor.
It is.
So imagine a classic police surveillance stakeout on a suspect's house.
Okay, I like this.
In this scenario, the National Reconnaissance Office is the technical team that actually builds the high-powered binoculars and mounts them on the tripod.
That is a very fair comparison. They provide and maintain the hardware.
Okay, then the National Geospatial-Intelligence Agency is the team of detectives taking the photographs through those binoculars, analyzing the suspect's movements, measuring the tire tracks in the driveway, and mapping out the physical layout of the property.
Yes, they are analyzing the physical environment and the actions taking place within it.
And finally, the National Security Agency is the team sitting in the unmarked van across the street, holding the parabolic microphone, listening to the suspect's phone conversations, and tracking the Wi-Fi signals coming from inside the house.
That is a phenomenal analogy. That is exactly how the labor is divided among the triad.
It makes so much more sense when you break it down like that.
And understanding why it is divided that way is crucial for a joint force commander. No single agency has the complete picture.
Because they are all specialized.
Right. A visual image might show you a tank, but it won't tell you what the tank commander is saying on the radio. An intercepted radio call might tell you an attack is coming, but without a map, you don't know where the enemy is physically located.
So the Joint Force Commander really has to weave all three together.
Exactly. The Joint Force Commander needs that inter-organizational cooperation to achieve what military doctrine calls space domain awareness.
Let's unpack space domain awareness, actually, because honestly, it sounds like a buzzword for just knowing where the satellites are in orbit.
It's a massive misconception that it is just space traffic control.
It's not.
Not at all. Space domain awareness goes far beyond space surveillance, which is simply tracking physical objects to avoid collisions. Space domain awareness means understanding the intent, the motive, and the predicted actions of adversaries across all segments of the space architecture.
Okay, what are those segments?
Well, it includes the satellites in orbit, certainly, but it also includes the ground stations on Earth that control those satellites and the invisible data links connecting the two.
So it's the whole ecosystem.
Yes. When a Joint Force Commander can fuse the visual intelligence from the geospatial team with the intercepted signals from the signals intelligence team, all enabled by the hardware team, they achieve a level of combat assessment that a single discipline simply cannot provide.
Wow.
You don't just see the enemy, you understand their posture, their communications, and their intent.
It is the ultimate fusion of seeing, listening, and mapping, all happening from hundreds of miles above the Earth.
It really is.
So now that we know who operates these systems and why they have to work together, I want to dive into the actual physics of how these satellites see the battlefield. Because as I was reading the United States Army Space Reference text, it became very clear that a satellite sensor is vastly different from the standard camera you have on your smartphone.
Oh, vastly different. To understand how a satellite sees, we have to rethink what seeing actually means. We have to talk about the electromagnetic spectrum. Human eyes evolved to see a tiny, tiny sliver of that spectrum, the wavelengths that the sun outputs most abundantly, which we call visible light.
Right. Red, orange, yellow, green, blue, indigo, violet, the rainbow.
Right, but the universe doesn't stop at the edges of the rainbow. Everything in the universe emits or reflects electromagnetic energy across a much wider range, from incredibly short, energetic gamma rays and X-rays, all the way down to very long, slow radio waves.
And satellite sensors are designed to capture those invisible waves that our eyes completely ignore.
Exactly.
The text contrasts two specific types of visual imagery that these sensors collect: panchromatic and multispectral. Let's start with panchromatic. That is basically high-resolution black and white imagery, right?
Essentially, yes. The prefix pan means all, and chroma means color. A panchromatic sensor captures a broad range of visible light all at once, without separating it into individual colors.
Like catching all the light in one go.
Exactly. Imagine taking a bucket and catching all the rain falling from the sky, regardless of whether the drops are big or small. Because the sensor is gathering so much light across that broad band, it can achieve very high spatial resolution.
Oh, it's really sharp.
Extremely sharp. It gives you those incredibly crisp, detailed black and white images where you can see individual vehicles, the distinct outlines of buildings, or the painted lines on a runway.
It is great for seeing the shape of things.
Yeah.
But if you want to see things that are literally invisible to the human eye, you need multispectral imagery. And this is where the physics absolutely blew my mind.
It's incredible science.
Multispectral sensors capture data in multiple, very specific, narrow bands of the spectrum.
They slice the spectrum up. Instead of one big bucket, they have many tiny, perfectly calibrated buckets, each only catching a very specific wavelength of energy.
And the military applications for this are profound, especially when dealing with camouflage and concealment.
Oh, absolutely. Let's look at the near-infrared band as an example.
Okay, so this is light that is just past the red edge of the rainbow. We can't see it, but we can feel it as heat.
Actually, you are thinking of the thermal infrared band, which we feel as heat.
Oh, my mistake.
Near-infrared is closer to visible light. We can't see it, and we can't really feel it. But the natural world interacts with it constantly. For example, chlorophyll, the chemical in actively growing vegetation that allows plants to photosynthesize, reflects near-infrared light incredibly strongly.
Okay, I think I see where this is going.
To a sensor tuned to the near-infrared band, a healthy, living forest glows like a neon sign.
So imagine an adversary parks a tank in the middle of a dense forest. To hide it, they cover it with advanced camouflage netting that is painted the exact same shade of green as the surrounding leaves.
A classic tactic.
To the human eye, or even to a sharp panchromatic satellite sensor, it just looks like a continuous sea of green canopy, right? The shape of the tank is hidden, and the color matches perfectly.
The human eye is easily fooled because the paint is mimicking the visible wavelength of the leaves. But the multispectral sensor, looking at the near-infrared band, isn't looking at green paint. It is looking for chlorophyll.
Wow.
The real, actively growing trees will glow brightly in the near-infrared spectrum, but the green paint on the synthetic camouflage netting, it contains absolutely no chlorophyll.
It's just chemicals and dye.
Exactly. So in the near-infrared image, the forest is glowing, but the camouflage netting appears as a stark, dark, non-reflective void. It stands out like a black hole against a bright background.
That is wild.
The sensor defeats the camouflage not by having a sharper lens, but purely through the physics of light reflection.
It is literally happing the spectrum to reveal what the enemy thought was perfectly hidden.
That's a great way to put it.
But capturing that specific data depends entirely on the physical engineering of the satellite itself. And the text lays out 4 types of resolution, 4 pillars that dictate exactly what a satellite is capable of doing.
And those 4 pillars determine everything.
Let's walk through them because they're so important. The first one is spatial resolution.
Spatial resolution is what most people default to when they think of image quality. It refers to the physical size of the area on the ground that is represented by a single pixel in the digital image.
So if I'm looking at an image on my computer screen and I zoom all the way in until the image becomes a bunch of little colored squares.
Exactly. Each one of those squares is a pixel. If a satellite has a spatial resolution of 1 meter, it means each one of those individual pixels represents a 1 meter by 1 meter square of physical real estate on the surface of the Earth.
Okay.
The smaller that number, the finer the detail you can resolve.
So a half-meter spatial resolution gives you 4 pixels in the same area that a 1-meter resolution gives you just 1. You get exponentially more detail.
Precisely. You go from seeing a blob that might be a car to seeing the windshield and the shape of the trunk.
That makes perfect sense. So that covers the clarity of the image. The second pillar is spectral resolution. We touched on this with the multispectral discussion, right?
We did. Spectral resolution refers to the number and the width of the specific electromagnetic bands the sensor can collect.
So a panchromatic sensor has poor spectral resolution because it just lumps a massive wide band of visible light together into one bucket.
Right. And a multispectral sensor has better spectral resolution because it divides the light into maybe 4 or 8 specific buckets like red, green, blue, and near infrared.
Okay.
But then you have hyperspectral sensors, which have incredible spectral resolution. They divide the electromagnetic spectrum into hundreds of incredibly narrow, precise bands.
Wow. What does slicing it that thin actually do for a military planner?
It allows you to identify specific materials based on their unique electromagnetic signature. Every material reflects light a little differently.
Like a fingerprint.
Exactly like a fingerprint. With hyperspectral imaging, you aren't just distinguishing a real tree from a fake tree. You can distinguish between different types of soil, which tells you if the ground can support the weight of a tank column.
That is so specific.
Or you can identify the specific chemical composition of a plume of smoke coming from a factory, which might tell you if they are manufacturing civilian fertilizer or chemical weapons.
You are doing chemistry from orbit.
Essentially, yes.
Okay, the third pillar is radiometric resolution. This one felt a bit more abstract in the reading.
Radiometric resolution is the system's ability to distinguish subtle, minute differences in energy. Think of it as the sensitivity of the sensor.
Okay.
A simple analogy is a box of crayons. If a sensor has low radiometric resolution, it is like having an 8-pack of crayons. You have red, you have blue, you have black. If you are drawing a picture, you can only use those 8 distinct shades.
But the real world doesn't operate in just 8 colors.
Precisely. A sensor with high radiometric resolution is like having the giant 128-pack of crayons. It can detect dozens of incredibly subtle shades of red or gray.
How does that help militarily?
In military terms, a sensor with high radiometric resolution can detect a very faint, thermal heat signature of a recently turned-off engine against a slightly cooler background of a dirt road. It provides a contrast that a lower resolution sensor would just blur together into a single, meaningless shade of gray.
It detects the whisper of energy, basically.
I love that phrasing. Yes, the whisper of energy.
Which brings us to the fourth and final pillar, temporal resolution. This measures time. It is how often the satellite can revisit an image the exact same geographic spot on the Earth.
Right. Orbital mechanics dictate that satellites don't just hover over one spot unless they are geostationary, which is incredibly high up and much less useful for high-resolution imagery.
They're too far away.
Exactly. Most reconnaissance satellites are in low Earth orbit, meaning they are constantly circling the globe. If a satellite is in an orbit that brings it directly over a specific city, say once every 3 days, its temporal resolution for that specific city is 3 days.
Okay, I have to push back on this concept because it seems counterintuitive to everything we want from technology.
How so?
Well, if we have a satellite with spatial resolution so perfect that it can read a license plate or identify the exact make and model of a truck from orbit, why does it matter if it only passes over once a week? Doesn't that incredible eye-watering spatial resolution trump everything else?
That is a very common assumption, particularly for people who don't plan military campaigns.
Guilty as charged.
But in a tactical context, it is a dangerous assumption. Let's connect this to the fluid reality of modern warfare. The defining characteristic of a modern battlefield is that targets move.
They don't just sit there waiting to be photographed.
No, they absolutely do not. Imagine an adversary has a mobile ballistic missile launcher, a massive truck that can drive into a clearing, launch a devastating weapon, and drive away in minutes. If your incredibly sharp, perfect spatial resolution satellite images that clearing on a Tuesday and takes a beautiful picture of that missile launcher, well, that is fantastic intelligence for Tuesday. But if the satellite's temporal resolution is poor and its orbit won't bring it back over that clearing until next Tuesday, you have a massive blind spot.
Because by Wednesday morning, that missile launcher could be hundreds of miles away, hiding in a totally different forest.
Exactly. If the target moves, all those perfect high-resolution pixels are essentially showing you history, not the current reality.
Oh, I see.
High spatial resolution is completely useless if the temporal resolution doesn't match the speed of the adversary's operations. This is why temporal resolution, the revisit rate, is often the single most critical factor for a military planner.
And recognizing this limitation drove a massive engineering innovation, right? Off-nadir viewing.
Yes, off-nadir viewing changed the game.
Let's explain off-nadir. Nadir is the term for the point directly below the satellite. Straight down, correct.
Yes. In the early days of space reconnaissance, satellites largely had to fly directly over a target, pointing straight down at the nadir to get a clear image. It was like wearing blinders. You only saw the strip of Earth passing directly beneath your feet.
So if your orbit took you 50 miles to the east of the target, you just missed it.
Completely made it.
Which meant you had to wait days for the Earth to rotate beneath your orbit until your track finally aligned directly over the target again.
Right. But modern systems are directional. They don't just stare straight down. Using complex internal gyroscopes and momentum wheels, the engineers can physically tilt the entire spacecraft or slew the optical sensors to look side to side, far away from their ground track.
So instead of wearing blinders, the satellite can effectively turn its head and look hundreds of miles to the left or right.
Which drastically improves the temporal resolution. Because the satellite has such a wide field of regard on each pass around the Earth, it doesn't have to wait to be directly overhead.
It can just glance over.
Exactly. It can image a target from an oblique angle on Monday, image it from a different angle on Tuesday, and again on Wednesday. It turns a narrow strip of coverage into a massive, sweeping swath of surveillance.
It dramatically increases the persistence of the observation, which transitions us to a really uncomfortable truth for the United States.
It is an uncomfortable truth.
We used to have an absolute monopoly on these incredible spatial and temporal capabilities. We had the budget to build the most sensitive sensors, the rockets to achieve the best orbits, and the massive triad of agencies to process the data.
We were unmatched for a long time.
But reading through the deep dive materials, it is glaringly obvious that the sky is getting crowded, that historical monopoly is completely gone.
It is a profound shift in the global balance of power. For half a century, the asymmetric advantage of the United States was the ability to see the world while remaining largely unseen ourselves. But we are now in the era of the democratization of space. We are seeing a massive, accelerating global proliferation of space-based imagery systems. The technology to build high-resolution sensors and reliable rockets has become cheaper, smaller, and far more globally accessible.
Let's start with the commercial sector because they are driving a lot of this democratization. The text highlights United States commercial satellites, specifically mentioning systems like Worldview 3.
Worldview 3 is a fascinating case study. It is a commercial satellite, meaning it is owned by a private corporation, and the imagery it produces is a product sold on the open market.
Anybody can buy it.
Yes, yet its physical capabilities rival what was considered highly classified, closely guarded military technology just a couple of decades ago. It provides panchromatic spatial resolution down to roughly 1/3 of a meter.
Wait, 1/3 of a meter? That is roughly 12 inches per pixel.
Right.
That is enough to distinguish between a pickup truck and an SUV from space. And anyone can buy it.
Anyone with the money. And it also collects in multiple spectral bands, so it has that multispectral capability we discussed. More importantly, because it is part of a larger commercial constellation, a network of many satellites working together, the temporal resolution is excellent.
So they can see the same spot frequently.
They can image almost any place on Earth multiple times a day.
And it isn't just United States corporations dominating this open market either. The reading points out that our allies are fielding phenomenal systems too, like France's Pleiades Neo constellation.
The Pleiades Neo system provides similar ultra-high-resolution imagery, operating at around 30-centimeter resolution. This is incredibly beneficial for alliance sharing, of course.
Right, we can share the data.
We can purchase or trade data with allied nations to supplement our own military intelligence. But from a broader perspective, it proves that the deep engineering know-how required to build these exquisite systems is no longer confined to American or Russian laboratories. The knowledge has spread globally.
But here is where it gets highly concerning for a military planner. The text doesn't just list allies and commercial companies. It critically discusses adversary capabilities.
Which is the real threat.
It mentions China's Gaojing satellites, which are highly capable optical systems, but it specifically highlights their GF3 satellite. What makes the GF3 so strategically important?
The GF3 is a critical leap in capability because it utilizes synthetic aperture radar. To understand why this matters, we have to go back to our discussion about the limitations of the electromagnetic spectrum. Remember when we talked about visible light and near-infrared light?
Right. If you have perfect optical spatial resolution and amazing multispectral sensors tuned to chlorophyll, but the target is covered by a massive thunderstorm, the satellite just sees the white, fluffy tops of the clouds.
Exactly. Visible light cannot penetrate water vapor. Optical sensors are passive. They rely on the sun to bounce light off the Earth and back up to the satellite. If a cloud is in the way, the light scatters.
So you're blank.
You're blind. But synthetic aperture radar completely bypasses this limitation. Instead of passively waiting for sunlight, a synthetic aperture radar satellite is active. It generates and beams its own powerful radio waves down to the Earth's surface.
And radio waves are much, much longer than visible light waves.
Because they're so long, they don't bounce off the tiny water droplets in a cloud. They pass right through the cloud, hit the metal of a tank or the concrete of a runway on the ground, and bounce back up to the satellite.
Like an echo.
Exactly like an echo. The sensor measures that backscatter the returning radio echo. It uses the forward motion of the satellite to mathematically simulate a massive miles-long antenna, creating an incredibly detailed image from those radio echoes.
Which means it doesn't care about the weather.
It provides its own illumination with radio waves, so it can image perfectly in the dead of night. And because the waves ignore water vapor, it can image perfectly through thick clouds, heavy fog, and even light rain.
So the fact that China is fielding robust synthetic aperture radar capabilities like the GF3 means they have achieved persistent, all-weather, day or night surveillance.
They don't have to wait for a sunny day to see what we are doing anymore.
And the reading also mentions Russia's Rizers P4, which adds another layer of high-resolution, multispectral capability to an adversarial nation.
Yes, it does.
When you stack all of this up, the commercial constellations, the allied systems, the adversary optical and radar satellites, what is the ultimate strategic implication here?
The strategic implication is a fundamental paradigm shift. The asymmetric advantage of concealment on a macro scale has completely evaporated.
Wow.
Commercial entities now sell high-quality, high-resolution imagery to anyone with a credit card, an internet connection, and the desire to look. If a non-state actor or a smaller adversarial nation cannot afford the billions of dollars to build their own space program, They don't have to.
They just bypass the engineering entirely and buy the data.
Exactly. They just buy it.
The simplicity of that is terrifying. We are operating in a modern environment where a hostile actor doesn't need decades of aerospace research, a massive rocket launch facility, or a triad of intelligence agencies to track our troop movements or monitor activity at a naval port.
No, they don't.
They just need a Wi-Fi connection and a budget.
It forces a complete systemic rethink of operational security. If you are a commander moving a division of tanks or loading an aircraft carrier, you have to assume that someone, somewhere, is looking at you.
Always.
Always. And that someone might be a commercially motivated company that is perfectly willing to sell that picture to the highest bidder, whoever that may be.
Okay, so the enemy can see us, and we can see them, no matter the weather, no matter the time of day. But seeing the physical battlefield is still only half the equation.
It's just the visual layer.
If an adversary is hiding their critical assets under thick, impenetrable physical cover, say, inside a deeply buried reinforced concrete bunker, or under a triple canopy jungle where even synthetic aperture radar struggles to get a clear bounce, we have to rely on what we can hear.
We have to listen.
We have to transition from the cameras to the microphones. So let's talk about listening from orbit. Signals intelligence.
Signals intelligence is an incredibly fascinating and deeply mathematical discipline, because you are hunting for something entirely invisible. You aren't taking pictures of objects. You are hunting for emissions of energy.
And as the reading clarifies, signals intelligence is not just one thing. It is an umbrella term that breaks down into three very distinct, highly specialized subdisciplines.
Correct.
The first subdiscipline is communications intelligence.
Communications intelligence is exactly what it sounds like. It is the interception and exploitation of foreign communications. If humans, or computers acting on behalf of humans, are talking to each other using the electromagnetic spectrum, the communications intelligence team is trying to listen in.
This means intercepting a soldier talking on a handheld two-way radio, or tapping into microwave transmissions carrying phone calls between two military bases, or capturing the encrypted data links connecting a drone to its pilot.
Yes. The goal is to capture the signal, decipher the language or break the encryption code, and extract the meaning. You want to know what the enemy is saying to each other.
The second subdiscipline is electronic intelligence. How does that differ from intercepting communications? Because aren't all of these just electronic signals?
They are all electronic signals, but electronic intelligence is strictly focused on non-communications emissions. You aren't listening for voices or data files.
So what are you listening for?
The classic, most vital example is tracking adversarial radar systems.
Because a radar system is essentially a giant flashlight, but instead of light, it shines radio waves to look for airplanes.
Exactly. A radar antenna doesn't transmit language. It transmits a massive pulse of energy to bounce off a target. Electronic intelligence sensors in space are designed to listen for those specific, invisible radar pulses sweeping across the sky.
Okay.
By capturing that pulse and deeply analyzing its characteristics, the specific frequency it operates on, how fast the pulses repeat, and the sheer power of the signal, an analyst can determine exactly what type of radar it is.
So they can look at a squiggly line of data and say, that isn't just a radar. That is the specific targeting radar for a surface-to-air missile system.
Yes. They categorize the weapon system purely by the invisible hum it gives off. And more importantly, by intercepting the signal, they can pinpoint exactly where that missile system is located on the Earth.
Which allows commanders to either avoid that airspace or target the radar for destruction.
Exactly. You are mapping the threat without ever seeing it visually.
That's amazing. Now, the third subdiscipline under the signals umbrella is foreign instrumentation signals intelligence. This one sounds incredibly dense and technical.
It is arguably the most technical of the three because it deals with the language machines use to talk to other machines during development and testing. Foreign instrumentation signals intelligence involves collecting the raw telemetry data that a machine broadcasts to its engineers.
Can you give me an example of how that works in the real world?
The prime example is a foreign ballistic missile test. When an adversarial country launches a brand new experimental missile, that missile has hundreds of internal sensors. Throughout its flight, it is constantly broadcasting a stream of data back to the engineers on the ground.
Like it's vital signs.
Exactly. It is transmitting its exact speed, the internal temperature of the engines, the fuel pressure, the exact millisecond the stage is separate, and the trajectory of the warhead.
It is essentially live streaming its own physical checkup.
That's a perfect way to describe it. If our satellites can intercept that telemetry broadcast from space, we don't have to guess how fast their new missile is or how far it can fly. We intercept the exact data their own engineers are reading.
That feels almost like cheating.
It's a massive advantage. We can learn exactly how capable their new weapon is, its strengths, and its vulnerabilities, sometimes even before they have finished their testing program.
That is an incredible intelligence advantage. And the text provides some fascinating real-world examples of how this signals collection is evolving, specifically noting that it isn't just military signals anymore. The commercial sector is heavily involved.
Very much so.
The reading mentions the automatic identification system and the automatic dependent surveillance broadcast. What exactly are those and why do they matter?
These are globally mandated tracking systems built purely for civilian safety and collision avoidance. The automatic identification system is used by maritime vessel traffic.
For ships.
Right. International maritime law requires almost all large commercial ships, cargo vessels, oil tankers, cruise ships to constantly broadcast a radio signal containing their identity, their exact GPS position, their course, and their speed.
So ships don't crash into each other in the fog or at night.
Right. And the automatic dependent surveillance broadcast system does the exact same thing for commercial aircraft. Every airliner is constantly broadcasting its altitude, speed, and heading.
To avoid mid-air collisions.
Exactly. Originally, these systems were purely terrestrial. The signals were meant to be picked up by other ships, other airplanes, or ground-based traffic control towers to prevent accidents.
But the signals don't stop at the control tower. They keep traveling up into the sky.
And that is the evolution. Commercial companies realized that these safety beacons are loud enough to reach space. So they launched constellations of small satellites equipped with receivers to intercept these signals from low Earth orbit.
Meaning, by tapping into these safety broadcasts, we can sit in space and watch every single cargo ship move across the ocean and every commercial airliner across the globe in absolute real time.
It is a live map of global commerce.
But I have a fundamental question about the physics of all this signals collection. When you think about it, the entire planet is just buzzing with radio frequencies. You have billions of cell phones, millions of Wi-Fi routers, television broadcasts, military radios, civilian radars. It must be an incredibly chaotic, deafeningly noisy environment.
It is a cacophony.
How do we physically isolate and catch these specific, quiet signals from orbit?
That is the great ongoing engineering challenge of signals intelligence. It is an exercise in extreme physics and mathematics. First, for a satellite to collect a signal, that radio wave must be able to propagate to physically travel through the Earth's atmosphere, through the ionosphere, and reach orbital altitudes without losing all its energy.
Do all radio waves make it to space?
No, definitely not. It depends entirely on the wavelength. Some frequencies are completely absorbed by the atmosphere. Others hit the ionosphere, a layer of charged particles high in the atmosphere, and bounce straight back down to Earth.
Oh, like shortwave radio.
Exactly. This is how shortwave radio works. It bounces around the globe. But for the specific frequencies that do punch through the ionosphere and leak out into the vacuum of space, the satellites are waiting with highly sensitive, incredibly directional antennas.
But once the satellite catches the signal, you still have to figure out where it came from. The Earth is huge.
And this is where the processing comes in. A single satellite catching a signal can tell you what the signal is, but it has a hard time pinpointing exactly where it originated.
Because it just knows it heard something.
Right. However, if you have a constellation of multiple signals intelligence satellites in orbit, and they are networked together, they can use physics to triangulate the source.
How does that triangulation work?
Imagine you are standing in a city and you hear a police siren. Your brain calculates where the siren is based on which ear hears the sound first and how loud it is in each ear.
Right.
The satellites do the exact same thing on a planetary scale. If 3 different satellites detect the exact same radar pulse from the ground, but satellite A receives it a fraction of a millisecond before satellite B and a millisecond before satellite C. Massive computers on the ground calculate that time difference of arrival.
Oh, so using the speed of light, they calculate the distances based on the time delay and draw intersecting circles.
Exactly. Where the circles intersect is the exact location of the radar system. So capturing these emissions doesn't just let us listen. It allows us to precisely geolocate enemy jammers, characterize the capabilities of threat systems, and literally map out the invisible electromagnetic environment.
We can see the web of adversary communications and sensors as clearly as a geospatial analyst sees a physical building.
We really can.
Okay, let's take a breath and synthesize everything we've covered so far. We have optical cameras that can slice the spectrum to see actively growing leaves and defeat camouflage.
Yes.
We have synthetic aperture radar that can beam radio waves through thick clouds to see in the dark.
Right?
We have antennas that can map out entire radar installations and intercept missile telemetry just by listening to the static leaking into space. It sounds like we have achieved a literal godlike level of omniscience.
It does sound like that, doesn't it?
It does. But the deep dive reading is very careful, almost cautionary, in providing a reality check here. These systems are incredible, but they are not magic.
No, they are not magic.
For military planners, understanding the blind spots and limitations of space-based intelligence, surveillance, and reconnaissance is just as critical, if not more so, than understanding the capabilities.
Absolutely. The greatest danger in military strategy is hubris, the assumption that your technology is infallible and all-seeing. Space systems, for all their complexity, have several glaring, unavoidable limitations dictated by the laws of physics and logistics.
Let's get into those limitations. The first and most significant limitation is predictability.
Yes, because satellites don't fly like airplanes. You can't just turn the steering wheel.
Or they're stuck.
Exactly. Satellites are bound by Kepler's laws of planetary motion and orbital mechanics. Once a massive reconnaissance satellite is inserted into orbit, its path is incredibly rigid and predictable. It is essentially falling around the Earth on a set track.
Even with little thrusters.
While they have small thrusters for minor orbital adjustments or avoiding debris, they cannot drastically alter their course.
Meaning, an adversary doesn't have to guess where our cameras are. They know exactly when they will be overhead.
Precisely. If you can mathematically calculate a satellite's orbit, and there is open source software available online that can track almost any unclassified object in space, you have its complete schedule. Wow.
You know its altitude, its trajectory, and the exact window of time it will have a line of sight to a specific location on Earth. Adversaries study these schedules obsessively and practice extensive denial and deception operations based entirely on this predictability.
Give me an example of how they use that predictability against us.
Okay, imagine an adversary is assembling a sensitive mobile missile launcher. If their tracking software tells them that a highly capable optical imaging satellite will be passing over their secret base at exactly 1400 hours, they adapt.
What do they do?
At 1345, they simply stop working, move the missile and all the sensitive equipment into a hardened hangar, and close the doors. They wait in the dark. The satellite passes overhead at 1400, taking thousands of high-resolution pictures of an empty concrete tarmac.
And then?
At 1415, once the satellite has passed over the horizon, they open the doors and resume assembly. It is the ultimate high-stakes game of hide-and-seek, but it is played on a perfectly synchronized celestial timetable. The adversary isn't hiding from the camera. They're hiding from the schedule.
And that predictability forces planners to rely on other, less predictable intelligence sources, or to use off-nadir slewing to try and catch the adversary off guard from an unexpected angle.
But even then, they are fighting the second major limitation the text highlights, weather dependency. We touched on this earlier, but it is worth reiterating how massive of an impact it has.
It's huge, because the Earth is a very, very cloudy planet.
It is.
On any given day, a massive percentage of the Earth's surface is obscured by cloud cover. Traditional optical sensors and multispectral sensors, the ones that provide those beautiful, easily readable, high-resolution photographs, are completely blinded by this. They cannot see through the water vapor.
And while synthetic aperture radar solves this by penetrating the clouds, it has its own drawbacks.
Yes, definitely. Radar imagery is incredibly complex. It doesn't look like a photograph. It looks like a noisy black and white map of radio reflectivity.
It's hard to read.
It requires highly trained specialists or advanced algorithms to interpret. Furthermore, we simply have fewer radar satellites in orbit compared to the massive constellations of optical satellites.
So the weather is basically free cover.
Exactly. A well-timed, lingering storm system over a target area can provide days of natural, impenetrable cover for an adversary to move troops or equipment without fear of optical observation. Nature provides the best camouflage.
The third limitation we need to discuss is data latency. We spent a lot of time talking about temporal resolution, the revisit time of the satellite itself. But latency is a slightly different concept in the intelligence pipeline. Right?
Totally different. Temporal resolution is how often the camera takes the picture. Data latency is the logistical nightmare of how long it takes for that specific picture to travel from the satellite in orbit all the way down to a tactical commander in the field who actually needs to make a decision.
It isn't an instant text message.
Far from it. When a satellite takes an image over a denied area, it often cannot transmit that data down immediately because there might not be a friendly ground station within its line of sight.
Oh, because it's over enemy territory.
Right. It has to store the massive data files on onboard hard drives. It waits until its orbit brings it over a friendly relay satellite or a secure ground station, and then it downlinks the data.
And even once the raw data hits the ground, it isn't ready to use.
It has to be routed through secure fiber optic networks to a facility, perhaps the National Geospatial-Intelligence Agency. There, supercomputers process the raw ones and zeros into an actual image.
That sounds time-consuming.
Then an analyst has to look at the image, identify the targets, write a report, classify it, and push it out through military networks to the tablet of a commander sitting in a command post halfway across the world.
That entire chain takes time. So information is literally only as good as its age. If the geospatial team produces a highly detailed, perfectly clear, flawlessly analyzed image of an enemy armored convoy, but the process took 12 hours, that intelligence might be completely tactically irrelevant.
It usually is. If that convoy travels at 50 miles an hour, in 12 hours, they are 600 miles away from where the picture was taken. The intelligence is perfectly accurate regarding the historical past, but it is dangerously useless for the tactical present. The commander is looking at a ghost.
This brings the entire conversation back to the military planner's perspective. When a planner is building a campaign, they cannot just rely on the magic of space.
They absolutely cannot.
They must constantly ask deeply critical defensive questions. They have to ask, what is the threat force's capability to access commercial imagery? Are they currently using their credit cards to buy satellite pictures of our troop buildups?
And defensively, they have to consider denial and deception. How do we hide our own critical assets from their predictable satellite passes? Can we spoof their signals intelligence collection?
And offensively, a planner must ask, can we actively deny the adversary access to their space-based collection?
That's the real trick.
But how do you deny access to space without shooting a missile into orbit and creating a massive debris field?
You target the links. Can we use electronic warfare to jam the downlinks between their satellite and their ground station so the pictures never reach the analysts?
Wow, okay.
Can we use ground-based high-energy lasers to temporarily blind the delicate optical sensors on their imaging satellites as they pass overhead? Can we execute cyber attacks against the terrestrial ground stations that control the satellites?
Which leads us to a crucial, overarching summary point. You cannot view the space domain in isolation.
Not at all.
The balance of power in space operations requires constant, seamless, intricate integration with the terrestrial and cyberspace domains.
It is an inextricably linked ecosystem. To protect our orbital assets and achieve the joint forces' objectives, we have to physically protect the terrestrial ground stations that control the satellites.
Right, the buildings on the ground.
We have to ruthlessly secure the cyberspace links that transmit the data between the triad agencies, and we have to physically protect the massive launch facilities that get the satellites into orbit in the first place.
Because if the ground station goes dark, the billion-dollar satellite in orbit is just a useless piece of metal.
It's just space junk at that point.
It truly puts the sheer scale of space-based intelligence, surveillance, and reconnaissance into perspective. It is staggering. We are talking about constellations of incredibly fragile billion-dollar machines traveling at 5 miles a second through a radioactive vacuum.
They are dodging micrometeorites and space debris, all while coordinating seamlessly with ground stations across the globe.
And it all relies on the massive, daily interorganizational cooperation between the Reconnaissance Office building the hardware, the geospatial analysts interpreting the pixels, and the signals analysts decoding the invisible waves.
It is an absolute marvel of human engineering, logistical coordination, and applied physics.
But as we've seen throughout this deep dive, it is a marvel that is rapidly becoming available to the entire world. The high ground is getting incredibly crowded, and the absolute monopoly on overhead surveillance is history.
The skylight is open, and everyone is looking down.
Which leaves us with a final provocative thought to ponder as we wrap up our exploration of the space domain. As space becomes increasingly democratized and commercialized, we are rapidly approaching an era where both sides of a conflict might achieve near-perfect, persistent overhead surveillance.
It's a very real possibility.
When anyone can buy a half-meter resolution satellite image of their enemy from an app on their phone, the element of physical surprise on a strategic macro scale is essentially disappearing. You cannot hide the buildup of an army anymore.
No, you really can't.
So here is the question you have to ask yourself. Will the wars of the future be won not by the side with the sharpest cameras in orbit, but by the side with the most brilliant terrestrial deception?
That is the big question.
Will victory go to the force that builds the most convincing physical decoys, spoofed electronic signals, and the most advanced artificial intelligence to filter out the noise and figure out what is real and what is an illusion, designed specifically for the camera?
It is a fundamental question of deception versus detection, and it is a question that every military strategist is going to have to answer in the very near future.
Well, thank you so much for joining us for the Doctrine Deep Dive. We hope this exploration of the ultimate high ground has shifted your perspective on how we see and how we listen to the world from above. Until next time, keep looking up.